So let's talk about ellipses in this video. And when I say ellipses, I mean ellipses thought of as conic sections. In our definition in the notes, we said that a point P, we'll call it P, let's draw it over here, P, whose coordinates are, say, x, y. This point lies on an ellipse with foci, or focuses, F1 and F2, if the sum of the distances between P and F1 plus the distance between P and F2 is equal to a constant. So this is the defining property of the ellipse. In terms of the picture over here, we would say that the sum of this, the length of this line plus this line, these are the lines that connect the foci to the point P. This sum remains constant. The lengths of F1P and F2P can change as we move around the ellipse. So maybe we move over to the second quadrant somewhere, call this point P2. But the idea is that the sum of the lengths of these line segments that connect these, the sum remains constant. Okay, the sum of the lengths is constant. Now, in this lecture, what we like to, so number one, this is what we mean when we define the ellipse this way. So this is a geometric definition of the ellipse. What we'd like to do now is try to identify, if we know the ellipse, if we're given the ellipse, can we identify the foci? So remember these points F1 and F2, these 2 points, these are the fixed points. They don't move. They're not on the ellipse, but they are vital to describe or define the ellipse. And these are the fixed points. These are called the focuses or foci. Foci is the plural of focus. All right, so like I said in these notes, what we would like to do is try to find a formula to describe the coordinates of these points F1 and F2. I've drawn this ellipse so that it looks like the major axis is in the direction of the x-axis and the minor is in the direction of the y. And so when I say those words major and minor, so the major axis, this is the longest axis. So there are two different axes of this ellipse, and the minor axis is the shortest. Okay? Now, these two axes have certain properties. Number one, I have aligned this so that the origin is right in between, dead center between the two foci. And we can say, okay, this point over here on the edge of the major axis is at a point A, 0. And so A we call the semi-major axis. Now A is a number, but in the book the convention is to call this the semi-major axis. It's half the length of the major axis. Similarly, this point up here where the ellipse intersects the y-axis, this point would be, say, 0B, and B is called the semi-minor axis. Okay, and what we really want to do is we want to find coordinates for the foci. Notice the foci in this setup are both on the x-axis. And so let's just find the coordinates of F1, and by symmetry the coordinates of F2 will just be the opposite. So F1's coordinates, it's on the x-axis, so its y value is 0, and the height of the x value of the point, we'll say, is some number c, and our job here is to find c. Now before we actually find c, we want to do a little more setup. So the first thing I'm going to do is I'm going to create a right triangle that connects F1, the focus F1, to the point 0B. And then look at this. This now makes a right triangle. So the reason I've done this is because I want the right triangle. It's a right triangle where the vertical side length here is B. Okay, that's just the semi-minor axis. The base of this triangle, this is what we've called C. That's what we want to find, the length of the base. And the next question becomes, what is the length of this side here? And to answer that question, what we can do is we can remember the definition of our ellipse. So if we connect this segment here as well to add to the same point to the focus F2, then we know, by the way, these two are, everything is symmetric here, right? So the lengths of these two segments, let's just call this question mark, let's call this capital A, for the sake of just giving it a name. But what we know then is that the distance between F1 and this point up here, so let's call this point B up here, F1 and B, plus the distance between F2 and B this has to equal a constant. And not only that, but we know that these two side lengths are the same length, and so that constant must be a plus a. So that's equal to 2a. So that's the constant now. The constant that defines our ellipse in some sense, because for different constants we get different ellipses. On the other hand, we can look at the x-axis here, and if we think about this, building this in terms of the ellipse, let's say we're going to this point here. On one hand we have this short length right here, distance from F1 to that point, and on the other hand we have, let me choose a different color that we can tell the difference here. I don't have a whole lot of choices. I'll use red. The distance from here to here also, and those two get added together, right, to create this constant, which happens to be 2a. But when you look at this portion right here is the same as the portion that goes over here. Okay, and so when we add together the two lengths from the focus to the points on the x-axis, these just trace out the length of the major axis. And we know that the length of the major axis is twice what we call the semi-major axis, right? And so actually this constant 2 times capital A is equal to 2 times little a. And of course at this point we can cross off the 2's, and what we find is that the length of this magenta line here, the hypotenuse of our triangle, the length of this is actually not a question mark, it's equal to little a. Okay? So that was the setup just to get this triangle. Our whole goal is to solve for C. Once we have a right triangle and we know 2 of the sides, we can solve for C, no problem. But to do so, maybe we want to have a cleaner piece of paper. So let's move over here and redraw what we've got so far. So we've got this vertical segment, which goes through the point 0b. We've got this magenta line that connects that point to the focus. That has length A. And we've got our base, which is just the length from the origin to the focus. That has length C. And this is a right triangle by construction. And remember, our goal, we know, in this case, we're assuming that we know the minor, semi-minor, and semi-major axes. So we know A and B. And we also know that in this scenario, A is larger than B. Both of them are bigger than 0, but A is a little bit longer than B. The major axis is larger. And our job is to find C. Well, that can just be a function of the Pythagorean theorem, right? So the Pythagorean theorem, Pythagoras, tells us that what? In this scenario, it's A squared equals B squared plus C squared. It looks a little different just because of the way we named all these things. We didn't have the foresight to name these after what we expected the Pythagorean theorem to tell us. But in this scenario, we again want to solve for C. We know A and B, so we just have to subtract. So C squared in this scenario equals A squared minus B squared. Since A is larger than B, this number is positive, so it makes sense. And then the coordinates of our foci are just the positive and minus square root of this difference of squares. Okay, so our focus F1 is at, if we call this one C, call it positive, then our focus F1 is at C0, and our focus F2 is at negative C0, where again, this is the C that tells us the coordinate of the focus.